consulted at many of the usual suspects. Kristen is an active ham and loves to chase DX on HF with L-Craft K2, which she built while visiting her mother in Florida. She is an ARRL technical coordinator for the East Bay section, president of the Palo Alto Amateur Radio Association, PARA, and is active in many local clubs. And what she failed to give me, she's also a net control of the 9 a.m. talknet on Fridays, and she does one heck of a job. That's on the N685 repeater. So, without further ado, it's my pleasure to introduce Kristen McIntyre.
Thank you very much, Jim, and thank you all for coming. I'm going to look kind of funny here because I have two microphones. I want to give thanks to N6UOB Byron, who's videotaping the talk here today, and I want to thank you all for being brave enough to step through the door. It's a bit of an intimidating topic, and I'm going to kind of open up the top of your cranium and pour a lot of stuff in today, but it's going to be a hoot. We're going to try and cover a really big and interesting topic in a very short amount of time, but I want to try and give you a little bit of insight into something that's really cool. And the first thing I want to start off with is a little bit of what inspired me to do this. I was talking with my son about this, and I have this t-shirt. You may have seen me wear it from time to time. This is the t-shirt here, right here. This is it. See this t-shirt? These are very popular. I first saw them in the 1970s at MIT. I actually had the differential version of this t-shirt. This is an integral version. I got this one at MIT also when I visited sometime in the 80s. Because I lost my differential one. I don't know where the heck it went. Whenever I wear this t-shirt, something happens. I was wearing it at Apple recently, and some guy kind of went past me and then turned around and he said, "That's Maxwell's equations." And I said, "Yeah, you know what it means?" And I can give like a 3-minute spiel on this and tell you more or less what it means in 3 minutes, or just point to each equation and give you a quick rundown. But I thought, maybe I can do a little better. Maybe I can tell you and with a little more time what's going on here and give you a broader idea without going too deeply into the math, what I see when I see these equations, and not have to get you so confused that you just shake your head and walk out of the room. Another inspiration was a book that was given to me by NR7X Don, whom I don't see here today, called The Student's Guide to Maxwell's Equations. This is the book. It's a bit dog-eared because I take it with me when I travel sometimes because it's fun to leaf through. You see how short it is? It's only 130 pages. That's all there is to it. And it's very clear, very concise, has very few worked problems in it, but it's really wonderful. It just takes them apart and points out everything that's going on in there. And I thought, heck, I'll just read through this thing, it won't be very interesting. But no, it's a wonderful book. If you ever get a chance to get this book, it's on Amazon, by the way, Student's Guide to Maxwell's Equations. It's a really, really great book to get you through Maxwell's equations. Okay, so what the heck are these things? Well, they could be some kind of insane mathematics that you'll never, ever understand. But we don't think that's true, right? Right? They could be some kind of weird Rosetta Stone left by aliens, which I really doubt. They could turn into a fun parlor game that you can play at home, which you may be able to do after we get done here, I hope. It could be what's trending on Twitter, maybe so afterwards. But instead, they are 4 simultaneous differential equations that we can use to bound this subject that we're going to talk about. Some very, very pretty mathematics, actually. And some really interesting statements about the state of electricity and magnetism, electric fields and magnetic fields, and really nothing to fear. It seems really scary on the surface, but really, really nothing to fear. Okay? So with that, let's talk about one more thing I want to say before we dive in a little deeper. And I want to say that I present this to you not with hubris, but with great humility. A lot of people said when I started to do this, "Kristen, are you nuts? You really think you're going to do this in 45 minutes?" But no. Many other people said, "Yeah, let's see you do that. You're crazy." But what I really want to do is give you a feeling for what I experience when I see these things. Because to me, they have real meaning. I look at them and they speak to me in this way. And I want to see if I can speak to you in this way. And I'd love to get some feedback from you when we get through with all of this, see if they spoke to you a little bit, okay? And the last thing is we're obviously not going to cover everything. We're just going to touch the surface of some stuff, but hopefully we'll touch some useful stuff. So let's get rid of me and get to James Clerk Maxwell. Okay, so first thing, we're going to do some stuff like a little secret decoder ring. Remember Captain Midnight? Okay, so we're going to talk about a few of the symbols. We have to do a little bit of the math symbols, but I want to get it so that a few of these things will make some sense to you, so that when you see the equations, maybe a few of these symbols will click in your brain and give you some meaning, so that you can look at them and say, aha, I kind of remember what that might mean to me. And then you can map those to something in your brain that has some meaning. So with that, let's keep calm and carry on. All right? You ready? Ready to go?
Yeah.
All right, 45 minutes starts now. Okay, first some fundamentals. We need to learn a few things. All right, anybody know what a scalar is? A scalar is just a number, okay? It's a fancy name for a number. Just a plain old number. It's a value. Okay, now we're going to take that scalar and we're going to extend it to what's called a scalar field. Has anybody ever seen a temperature map on the weather report? A temperature map is an example of a scalar field. It assigns a number to every point in space. So for every point in space, there is a corresponding number. That's a scalar field. Okay, next thing we need to think about is a vector. A vector is a number of points. So we have some arrow pointing in a direction and some length assigned to the arrow. That would be its magnitude. Okay? Is that a cool concept? All right, now we're going to extend that, just like we did with the scalar field, to a field of vectors. This is a little more hard to visualize, but we have an arrow for every point in space. So we have a vector field, a field of vectors. Okay, and you can think of these like wind currents or currents in the ocean. So for every point in the ocean, for example, there is a force of the ocean that has a particular direction it's pointing and a magnitude of that force. Or the wind, same deal. Okay, make sense? Cool? All right, now we're going to go on to something a little harder. Scary integrals. Well, integrals look really scary, and in some sense they're a pain. And it's certainly no fun doing integrals at some level. But what they basically say is add. And what differentials say is subtract at some level. So when we do integrals, we add. When we do differentials, we subtract. So when you see the integral sign, think add it. And we have this fancy schmancy looking one with a circle in it, and that means add over some geometry. So that implies some geometric expression of this adding. And then we have these other ones that say d over dt. See that down at the bottom there? And that squiggly looking d is another kind of differential. That's a partial differential. We say partial t if we want to be fancy mathematicians. Okay, and that means find the difference, how something changes in time, for example. Okay, those are rates of change.
It's like that less toxic than DDT?
Yeah, okay. Yeah. Okay. Yeah. 10 points off. The middle one there is the del operator, and that's sort of a geometric version of subtracting. So we try to find the changes in geometry with that one, and that's for things like gradients and other more complicated versions of that. Okay? So that's a slightly more complicated concept than we were talking about with the vectors, but we can apply these things to vectors and vector fields and scalars and scalar fields. Okay? All right. Now we're going to launch into the first more difficult thing, divergence. Divergence is an operator that we can apply to a vector field to find out how much something goes away from something else, okay? It produces a scalar value for a scalar field.
Can I shut the back door?
Yeah, can we close the door? It's kind of noisy back there. Or maybe people can squeeze in a little bit. Can people move up in the aisle? Yeah, there we go. So With divergence, we try to find out if things are flowing away from a point or into a point, sort of like sources and sinks. And you can see from the picture here that we have a single point and things flowing away from the point. And it's asking this question, do things flow out or in? Another way to look at it is if you have like a box, and you look at the box, and do things flow, is the net flow into, or is there a net flow into or out of the box? If you look at a case like this, you can see that all the stuff that flows into the box flows out of the box. In a case like this, there's no divergence, because everything that flows in flows out. But if we change it a little bit, like this, you can see not as much stuff flows in as flows out. In this case, there is some divergence. Okay? Now I want you to keep that little model in mind as we move forward. Another thing that exhibits divergence is something like this, where we have a single point where things emanate from the point. So right in that center there, things are going out from the point. That's divergence. If we choose another point and look there, we'd have to examine it in detail to see for sure, but it looks like there might not be divergence at that point. Everything that's flowing into it is flowing out of it, maybe. Now divergence is mathematically well defined, so we'd have to look very carefully to make sure that there is no divergence, but it would appear as though there's no divergence at that point. Take another case like this, it would appear that there's no divergence here because things are circling around and chances are everything that goes in comes out at both of those points. Okay? So you get the general idea of divergence? Do things flow in or out, sources and sinks? Now I'm going to go to another concept. This is called curl. Okay? Curl is a little harder to visualize than divergence. Divergence seems more straightforward, at least to me it does. Curl is whether things rotate. Are things rotating at all? It takes vectors in and gives vectors out. And the vector points in the axis of rotation. So you can think about it as rotation around a point. And it's sort of like the way this ball might circulate in this vector field. But another way to look at it is if you have something like this, where you have, here's a two-dimensional flow. You see these vectors that might indicate the flow. If you put a little propeller in the middle of this, does that propeller spin? And how does it orient in the flow? And in this case, what do you think happens? Does the propeller spin? No, the propeller doesn't spin. So this doesn't curl. But if we change this such that some of the vectors are longer than the others, now what happens? It spins, right? So this has curl. And the curl actually comes out of the board, out of the screen. Okay? So the vector for the curl points out. So you get the idea? That's what curl looks like. Okay? Now if we look at something like that, we can see that this clearly has curl in the middle. But if we look out further, it probably doesn't have curl at a point out from the center. But we don't know. We'd have to actually do the mathematical operation to see if it really doesn't have curl further out. It might. But there's, again, a precise mathematical definition of what curl is, and we'd have to check it to see for sure.
And is that curl a vector that's going perpendicular in the z?
Out from the board.
Okay, but 90 degrees out? Or
Yeah, it's the axis about which a propeller might rotate. Okay? Now, here's another vector field, and this one was the one that we looked at with divergence, and chances are this has no curl. Okay, nothing would rotate in this field. And nothing would rotate further out, probably. Probably, if all of those arrows are the same size. If they're not, it might have curl. It's not clear. Again, precise mathematical definition, so we'd have to check for sure. Now here's one that's kind of interesting. You might think that any field that has curvature would have curl, but no. This is a field that exhibits divergence, and it's all curly. In other words, it's bent, but it doesn't have curl at all. So this field has lots of divergence, but no curl at all. So again, it can be sometimes counterintuitive. You have to think carefully about these things. So here are a source and a sink, very bent looking, and very divergent, but no curl whatsoever. Okay? So, one must think carefully. All right, I want to introduce another concept, and this concept is kind of weird. It's called a Gaussian surface. Now, a Gaussian surface is a mathematical tool. It's a tool we use to think about divergence and curl in a different way. Okay, I want to introduce a different way to think about divergence and curl. And it's a way that we can map this into a different world. And we use a thing called Stokes' theorem to transform one way of thinking about these equations into another. And there's two sub-theorems called the divergence theorem and the Kelvin-Stokes theorem. I don't want to get too much into that. But what you have to have is a closed surface. That means something that's completely enclosed. So some kind of bubble. Like a sphere is a good example of a closed surface, but it doesn't have to be a sphere. A sphere is very common. And I want to bring you back to remember the box we were talking about when we talked about divergence. Because that's the kind of thing we're talking about. That's a closed surface in 2 dimensions. Now, in order to think about these Gaussian surfaces, we have to talk about a thing called the surface normal. Now, the surface normal, it's a funny way of saying something that's perpendicular. So if we have a surface, some bubble or whatever, if we balance a plane on top, okay, if we balance a piece of plexiglass like on top of the surface, we find whatever is perfectly parallel with that surface. And we put something that's perfectly perpendicular to the plane, perfectly at right angles to the plane, and we make that thing 1 unit high. That's a surface normal. Okay, a unit normal. That means it's 1 unit high. That's a vector that points exactly right out of the surface of that thing. Okay? That's our unit vector. And if we do that at all points on the surface, we now have a thing that just points exactly out from that. That's a useful tool for us. Because what we want to do is we want to add up all the pieces of something that points out of that surface and points directly out of it. And we do that using a thing called the vector dot product. And the way I explained this to my son was I said the dot product is this thing that tells us how much of something is pointing in the same direction. So if it's pointing in the same direction with the dot product, if you have 2 vectors that point the same way, then the dot product is the same, is 1. But if it's pointing 90 degrees opposed, then it's 0. So if it's the same way, we get all the power of whatever it is that's pointing through, and if it's the different way, then we get none of it. And the closer it is, the more we get, sort of. Not exactly proportional as if it were a fraction, but you get the idea. Okay? It's the cosine, actually, it's a relationship. And if we add those all up over the surface of something, it turns out that we've actually recreated divergence. Okay? So we get this way of recreating the divergence just the way we did by putting that box around the arrows and seeing whether everything that comes in goes out. And what we get is this recreation in another way of looking at divergence. So we have 2 ways to look at divergence. Do things go, away from something and come back? Or when we sum them up around a box, do we get more coming out than coming in? Okay? That's 2 ways of looking at it. Now the next one is a little harder to visualize. This is called the Kelvin-Stokes theorem. And it's a bit harder to visualize, but I want you to just kind of bear with me here. We have another kind of surface where we draw a loop, any kind of loop. And if we draw a loop, and then we put any surface we want that covers what that loop encloses. Okay, so we do a loop, can be any shape we want, and then we have some surface that encloses that loop. And that surface can be any shape we want. If we add up the dot products around that loop, then the curl of all of those surface normals through the loop is equal to the dot products around the loop. So we find this weird way of recreating curl. It's another way of measuring curl. Okay, it's a lot harder, and sort of you look at this and you go, really? Is that really true? But it is. It is really true. It's a really interesting theorem. Okay, so Can you kind of see that? It seems like it shouldn't really be true, but it is. So if you just do that, it's called a line integral. We do this sum around the loop of the dot product, and we can actually get the curl of whatever goes through that loop. Okay? Very interesting thing. So we have two ways of looking at divergence and curl. And what this gives us is two forms of equations. Okay, now here comes the math part. So we have two ways of looking at things, differential and integral. And the reason that I bothered to go down this road is that, to me, when I look at these equations, I get two views of the world. I get the differential view and the integral view. The differential view tells me one thing, and the integral view tells me another thing. I get different insights. They are exactly the same. They really are. Mathematically, they're the same equations, but when I stare at them the first glance, they tell me a different story right off the bat. And that's an important thing I want to give you. And what we're going to do next is we're going to go through sort of the integral and differential forms and try and give you those insights one by one for each of the laws. Okay? Now, before we dive in, I have some alphabet soup for you if you're hungry. There's a few letters I need to give you because I might use them, and you might get confused if you don't know. You don't need to know all of these, but there's a couple you probably need to know. I might talk about them. The ones you really need to know are B and H and E and D. Those are important. So B and H are for magnetic fields, and E and D are for electric fields. And those two are kind of the same. Here are the relationships between some of them. B and H are related to one another. Those are both versions of the magnetic field. And E and D are both versions of the electric field. The other stuff isn't all that important. You know what current is, right? We're all hands here. We know what current is, right? J is another form of current. We've heard charge before, right? I hope. Charge? Yeah. Okay, and charge density is sort of like charge. So we sort of know what that stuff is. And you'll often see Maxwell's equations written in a couple of different forms because you can transform them back between different units by just dividing them or multiplying them by different things. And so you can write them in a whole bunch of different ways. So you get these kinds of transformations pretty easily. So if you look at different people's t-shirts, you get different versions of different things. But they're all the same. Like this t-shirt has the epsilon dot on this side, and other t-shirts have the epsilon dot on the other side. Okay. All right, you ready? You ready for the four laws? Okay, I'll give you sort of the 3-minute explanation that I give people on the t-shirt. Okay, here we go. All right, so the four laws, they start with Gauss's law. And this talks about electric fields and charge. Okay, and the shape of electric fields around charge. And then Gauss's law for magnetism. That tells us the shape of magnetic fields. Okay? Or it tells us what the magnetic fields are not shaped like. Faraday's laws for induction, one of the most interesting one of the four, tells us about time-varying magnetic fields' relation to electric fields, and how electric fields are sort of different in that domain. And then finally, Ampere's law tells us about time-varying electric fields and how currents are used to generate magnetic fields. Okay? We're done. You can all go home. Okay. All right. So, ready to dive in? Let's take a deeper dive. We'll start with Gauss's law. So, we have some charge, P. Let's say it's some positive charge. What's the shape of the electric field? Is it all squiggly? Is it run around in circles? Does it go out to the side? Who the heck knows? What happens when there's no charge around? Well, Gauss's law is going to tell us a little bit about that. So let's look at the differential form of Gauss's law. Gauss's law's differential form, to me, this is to me, it may say something different to you. It tells me that the divergence of the field results from charges, or they come together, or something like that. So always when you assign causality to these things, you're in dangerous waters. But they seem to go together. And I wrote 2 forms of that up there just to show you that, again, it's the same stuff. And just put the epsilon not in a different place, actually. But the electric field has divergence from the charge there. It's coming right out. See, that's the source. And when there's no charge there won't be divergence. So if that row thing there, that's the charge density. If that's 0, then there's no divergence. That's what that says right there. Okay, so if you put your secret decoder ring up there, you can see that del dot D, that's divergence. And that says if that divergence, that row there, that's charge. If that charge is 0, no divergence. Okay, and one of the things I wanted to point out while we're here is that one of the things that's easy to do with electric fields is make straight ones. If you just put charges next to one another, they resolve into straight fields really easily. That's a very easy thing to do. And like capacitor plates are good at doing it. If you line charges up, you can calculate very easily to come out nice and straight. So to me, that's the real easy insight from the differential side of Gauss's law. Now, if I look at the integral side, it doesn't really tell me a different thing per se, but it does help me to see some different thing. Okay, so we have the same setup. Here's our charge, here's our electric field, like that. But this time, we can put something around it, our Gaussian surface, remember that? And what it tells me is that if I add up all those surface normals around the outside, I can tell how much charge is inside. So if I add up all of those surface normals, and if I add them all up, I call it the electric flux. And if I see some electric flux in there and I measure it, I can tell how many charges are inside. And conversely, if I have some charges inside, I can tell how much electric flux is going to be coming out of that thing. Now, with the differential version of that law, that wasn't quite so obvious. But with this, it's really obvious because that E dot dA business up there, that's the electric flux. And that makes it really clear. And that Q over there, that's charge. It's very, very, very clear to me. Because of that integral sign, that says add. So when I add stuff up, that's charge. So you get an idea how this gives me a slightly different insight? So that's what the integral law says to me. And if there's no charge, there's no flux. So I take all the charges away, create some surface, there will be no flux, right? So that's the integral form of Gauss's law. Now for magnetism, we have some insights too. So it's a similar thing to Gauss's law. What's the shape of a magnetic field? What happens when there's no charge? And don't cringe. Gauss's law for magnetism, the differential form. What's the divergence of a magnetic field if you have a magnetic charge? What does it look like? Well, guess what? There are no magnetic charges that we know of. So guess what? No divergence. So the magnetic field doesn't diverge. It says so right there. Remember that divergence operator that we talked about? That particular equation right there says it right very clearly. Del dot D equals 0. That's your magic decoder ring. It says no divergence, period. End of story, as we say in New York. That's it. It's not going to diverge. Okay, so that tells you something very fundamental about the shape of magnetic fields. They simply don't diverge. Okay? It's a divergence-free field. So right now you've discovered something really interesting right there. Now, if we look at the integral form, we also see something slightly different, but also equally interesting. If we draw a Gaussian surface again, just as we did before, there's never a magnetic charge inside, which means that if we have a surface, there will always be net zero magnetic flux. And that even includes if you stick a bar magnet halfway inside and halfway outside. There will still be no net magnetic flux. Everything that goes out will come back in. Because no matter how tiny you slice up a bar magnet, it's always composed of magnetic dipoles. So the net magnetic flux will be 0. Isn't that interesting? So if you add up all the field lines coming in and all the field lines going out, they'll always add up to 0. And that wasn't so clear from the differential side, but it's really clear from the integral version. So that's a fascinating discovery, isn't it? So to me, that's just really, really deep. So no matter where you slice it, no matter what you do, no matter what shape you make this thing, it'll always be net zero. Anywhere in the universe. Fascinating, huh? Okay, now we're going to shift gears a little bit. Let's talk about Faraday's law of induction. This is the first time we're going to talk about dynamics. Up until this point, everything has been static. Everything's been unchanging. But now we're going to talk about stuff that changes. And this is the first time we're also going to link electric and magnetic fields. We've talked about them totally separately up till now. We talked about electric and then magnetic. But now we're going to link them. And we're going to talk about the shape when we link them too. And we're going to link them with time. Okay? Time is going to be the magic. It links the two. We're going to find out when we link them, they're not always the same shape. How about that? So if we look at the differential law, we can see what it tells us about shapes. So if we look up here, we see the top, I want you to look at the symbols a little bit. See the del cross E? That's curl. Remember the curl symbol? Del cross E means curl. So it says that curl is equal to, see the partial B, partial T? That's the time derivative. That means the change with respect to time. So that means that the curl of the electric field is going to be equal to the time change of the magnetic field. That means that curling electric fields happen when the magnetic field changes with respect to time. That means that the shape of the electric field fundamentally changes when it results, well, I want to say results from, I say when it occurs with a time-changing magnetic field. Okay? So you get the divergent electric fields from charges, you get the curling electric fields that occur with time-changing magnetic fields. They have two different shapes. Okay, so if you see the curl in the electric field, it's got to be coming from a magnetic field, or coming with one, anyway. So that's very interesting. You get two different shapes. And this has interesting implications for radio, which is why we're here in the first place, right? So keep that in the back of your mind. Now, if we look at the integral law, this one is really deep. This one has deep implications. Now, the integral law is where we get lots of interesting inventions. This is one that just brings them all to mind. If you look at this equation, on the left-hand side, well, from this you can see how to make motors and generators and transformers and all sorts of cool stuff. On the left-hand side, it says that the volts around a loop, okay, let's just start with that. The volts around the loop are equal to the time-changing magnetic flux through the loop. So if we can get a time-changing magnetic flux through some loop, we can get a voltage. We can create a voltage, which means that if we can push a magnet through some loop, we can get some voltage. And that means that we can do something like this, where we have a meter, and we push the magnet through there, and we actually see the meter change, which means we might be able to generate some power. Okay? It also implies that we might be able to make a transformer, because if we have the primary of the transformer and we put some AC on there, that might cause a time-changing magnetic field. We haven't figured out how to do that yet. We'll see that in a moment. But that might have some time-changing magnetic flux, and then that on the other side would create a voltage. Okay? So this has really interesting properties. And it turns out that this voltage around the loop is also a thing called the Lorentz force, the QB cross B force, which is the fundamental piece for making motors. And this is really, really deep stuff. This inspired Einstein to think about general relativity, this deep connection between the voltage around the loop and the Lorentz force, which is the force on an electron by a magnetic field that's moving at some velocity. It's very, very deep, deep, deep stuff. So motors, generators, all of this stuff, transformers, all come out of the thoughts inside this Faraday's law, induction law. It's very, very interesting. The most interesting and deep of the four laws in my mind. Okay? Now, let's move to Ampere's law. Now, up until this point, we've talked a lot about magnetic fields, but we have no idea how to make them. They just seem to be there, but we had no idea where they came from. But now we get to talk about how to make them. We talk about how to make them in both a static sense and in a dynamic sense. And we get to learn a little bit more about the linkage between electric and magnetic fields, and a little bit more about the shape. Okay? So, the differential form of Ampere's law looks like this. So, it says that the curl, that's the del cross H part, is equal to the current density. So if we have some current through a wire, it's going to be curling. And if we have a changing electric field, it's going to be curling. So what shape are magnetic fields? They curl. That's it. There's nothing left. They only curl. So magnetic fields always curl, contrary to electric fields. So that's why you ever seen pictures in the books of magnetic fields and they always look loopy? This is why. Because they're loopy. I'm loopy. You're all loopy from listening. But magnetic fields always curl. Okay? And it's this other picture here is to illustrate how it's a little more interesting and difficult to generate a straight magnetic field. You do it with a solenoid, which is a little bit harder to show mathematically, but not that hard actually. But you can make straight magnetic fields. It's a little harder, but doable. But the real key here that I want you to see is that magnetic and electric fields are really intrinsically linked to one another. We saw changing magnetic fields generating electric fields. Now we see changing electric fields generating magnetic fields, or at least occurring together. Generating is dicey business, okay? But you get the idea, right? So, and also, if you have some wire in the middle of nowhere, if you just have some current, some AC current moving through it, you're going to get both, you're going to get curling electric and magnetic fields coming off of it. Isn't that interesting, huh? And they're going to be in coming off in different directions and curling different ways. And it's kind of hard to visualize because this is all happening in 3 dimensions. These pictures do not do it justice in any way. Okay, let's look at the integral form. Now, the integral form is a little harder to visualize because now we're going to talk about loops of magnetism instead of loops of voltage. But this gives us a little more clear idea of how we make magnetic fields. So we do this thing, we talk about the Amperian loop. And we look at the equation here, and it just says that when we have a current, we get these loops of magnetic field, and we can measure them. We go around the loop, and we do this summing around the loop. We can see that we get the magnetic field around the loop. And we do get this interesting property where if we have a capacitor like this, and we charge the capacitor, for example, and we measure the field as we're charging the capacitor around some loop. And remember how we can put, any random surface across that loop and just measure and see what the curl is there? Well, it turns out that, sure enough, the curl of the field is equal to the current. Okay? Well, that looks fine when you're on the wire going into the capacitor, right? But what if you stick it in the middle of the capacitor? Then things get really weird. There's some current there, right? But that's this other part of the equation here with the partial d, partial t. That's the electric field part. And that is what's called the displacement current. And that's why it was called the displacement current, because it hangs out there with the other current term. And so you can see that it's all accounted for. So if you extend that Gaussian surface up into the plates in between the capacitors, you can measure the very same loop and the very same magnetic field. So it all still works, but that's a very clear way to kind of separate those two terms out. Okay? Everybody still with me? Not falling asleep. Okay, cool. You actually made it through the 4 laws. Okay? So we have these 4 laws in isolation, which are pretty cool. And they told us a lot about the shape of the electric and magnetic fields. And they've told us about the existence of electric charges and that magnetic charges are not there. And they've told us about the static and the dynamic parts. And the really interesting thing is that they've hinted about this deep relationship between electric and magnetic fields when time is changing them. And that's really interesting. But, what would happen if we wove them together? What interesting thing might come out of that? We have these 4 constraints on electricity and magnetism. They're all true at the same time. Okay? The dynamic parts are really, really interesting, aren't they? And it might take some serious vector calculus stuff, and I want you to bear with me. But it's not hard. If you can do algebra, you can follow this, okay? Can we do algebra? Okay, we can do algebra, so let's do it. Okay, you ready? Everybody cool? All right, let's do it.
Yes.
Okay, you remember the differential form, right? Aren't they beautiful? Can you appreciate that?
Yes.
Gorgeous. Okay, so we're going to gather our 4 equations. Here they are. Okay? And the first thing we're going to do is throw out the static parts. So there they are. We don't need those for what we're going to do. I mean, they're good. They're useful. We're going to throw them out for what we're going to do. Okay? So current and charge go away. We're going to retain the dynamic parts. Okay, we're going to combine what's left. But I want you to note that now the parts with the divergence all say no divergence. Keep that in your mind. That's useful for later. Okay, the curl equations are the most interesting though. So, ready for algebra? Here we go. So, we're going to combine the curl equations. Here are the curl equations. Keep in mind the relationships between B and H and D and E from up here. So here's the curl equations. Now we're going to do something, since the curl is a linear operator, we're going to take the curl of both sides of the equation. Take it from me, you can do this. Okay, so we're going to do that. Here's the curl of both sides. Got that? So we're cool. Now comes the tricky part. We're going to substitute one equation into the other. So when the top goes to the bottom and the 2 middle ones interchange, like that. And I want you to note that if I take the partial derivative of the partial derivative, that's partial squared over partial t squared. Okay? So it comes out like that. Okay, not hard, not hard. This is easy stuff. Okay, take my word for it. Okay, I'm going to carry this to the next slide. Got it? This is easy, easy, easy. Take my word for it. Okay, so same thing. Now, there's this cool vector calculus identity up the top here, and it says that the curl of A is equal to the gradient of the divergence minus this thing called the Laplacian. Okay? Wait, I'll decode it. It's okay. Don't panic. Okay. So, you notice that that looks like that. You got that? They look the same. Just different letters. Don't worry about the different letters. Okay. Now, don't worry about that. I'm serious. Okay. Now remember that there was no divergence, right? We saw that before.
Yep.
You know what that means? That ugly thing goes away. Bye-bye. So forget about that. See, one less thing to worry about. So we're going to take that double curl thing, and we're going to substitute it in, and stick that Laplacian business in there. See it? That del squared business. Oh, yeah. Okay. All right. So yeah, see it went. Oh, cool. All right. See it went in there. All right. And then we just rearrange things a little bit. And we came up with this thing called the wave equation. It sounds really scary, but it's not, because it tells us something really interesting. And I substituted something in there. I put this letter C in place. And this letter C, as it turns out, happens to be the speed of light. And Maxwell himself wasn't really sure. He asked some guys who were experimenting with the speed of light, could this be the speed of light? Is this similar to the numbers you're getting? And they said, yeah, it kind of is. And sure enough, it was, as it turned out, experimentally. It was just a guess on his part. And this equation describes something interesting. But what the heck does it really mean? So what it means, it tells us that radio might be possible. And if you look at that together with the curl equations, it tells us a little bit about the shape of what radio might look like, were it possible. So I think it is. We've demonstrated that, haven't we? It tells us that time-varying electric and magnetic fields, they kind of travel together in a perpendicular fashion. And they actually travel, yet again, perpendicularly to that. And these pictures do not do it in any way justice. This little movie I snagulated doesn't do it justice either. This just gives you a tiny, tiny, tiny bit more insight into what's going on, but doesn't really tell you anything about this thing called the Laplacian. This weird-looking operator says that things will tend to spread out in spherical fashion from a point. That's what the Laplacian means. This funny del squared A business, that means it's going to be spherical. And so it's going to do those two vectors, 90 degrees, spreading out in spherical fashion, is what that big mess up there says. At some speed that has to do with that C thing up there. Okay? But you see how you're beginning to decode it, even though it seems kind of mind-bending? You look at this and you say, okay, there's some electric field business here, changing with time. This means spherical. This means speed. Okay? Curl involved. Okay? Changing with time. Minus sign involved. Some change between electric and magnetic. Yeah. It's starting to make some sense, isn't it? Okay. So, you get the idea. That's the idea. But unfortunately, the pictures just don't do it justice. And, every picture you draw cannot possibly tell you how complicated it is. Because for every point in space, there are two vectors. So there's sort of like, 6 dimensions, 2 magnitudes. It's very, very hard to think about. And so, when you think about these fields, I have a very hard time trying to figure out what's going on. And then, there's this whole part of this that I didn't touch on at all called boundary conditions and how things interact with conductors. So when we put stuff in on a transmission line, for example, charges move around in these metals, and that changes how the fields are aligned, because the charges actually flow through these metals and change the parameters. For example, if you look at in a waveguide, electric fields will never be tangential to a perfect conductor. And this has to do with how the charges spread out in the conductor. And it's not so much a consequence directly of Maxwell's equation, but a consequence of the property of conductors themselves. And this is one of those things that if you study electromagnetics, you'll learn it or even just second semester physics at college, you'll learn this right away. And it's one of those simple things that you figure out. But it's very, very hard to visualize this stuff. But if you can start to see a little bit what the equations are telling you, you can start to visualize it in your head. These pictures don't do it justice. That's the point. And one other thing I want to mention about this is that you can change the C thing very easily by changing mu and epsilon, those two funny-looking Greek symbols. This not afterwards, this 0 thing, that implies that it's in a vacuum. And they don't have to be in a vacuum. You can change them. And then you change the refractive index. That's what that little thing there is. And then the waves will kind of slow down as they hit the thing. If they hit it dead on, they'll just sort of slow down. But if they hit it at an angle, they'll kind of bounce sideways and bang in some fashion. And that's what happens with ionospheric refraction and that sort of thing. But when you look at these equations, you can see you're changing that number right there. And that changes the spherical spreading again. So now you can kind of see where it pokes a stick at the map. Okay, and I'll give you one final little movie to look at, and maybe I'll give you a little bit of insight, I don't know. This was just the electric field on a dipole. It's very, very crude, but even this gives you nothing really. Just sort of magnitudes and spatial stuff, but no vectors at all. But even that is very, very rich.
And that's based on the direction of the electrons in which direction.
Okay? So you get the idea. So what have we learned? What have we learned? So Maxwell's equations, maybe not so scary as they were when you walked in the door, right? I hope so. Scarier? Sorry, I failed.
I'll go with the last one.
Okay, okay. I tried to get it less scary. You certainly didn't learn everything on this subject. You could spend years with this. But there is a way to kind of decode this a bit. I hope I gave you a little bit. If you look back at the slides, which I'll make available to anybody who cares to look at them, you can go back and pick up the decoder ring and maybe make a little more sense out of this stuff. I think the geometry helps you a bit. When I taught this stuff to my son, I used the geometry a lot. I think that helped him more than anything else, rather than just scribbling down the vector calculus, which I think is penetrable. But I think the geometry helps a lot, the differential geometry. And when you combine these equations, you get propagation, which I think is a very easy derivation that yields a wonderful result. And this is some really, really beautiful math. I mean, Maxwell's equations. And vector calculus itself is a beautiful subject, which was not Maxwell's invention. That was all for Heaviside. But that's a beautiful subject all on its own. If you're really interested in this whole subject, there's tons of stuff. I recommend this book. If you want just a terse explanation, 130 pages, it's not much. It's a great book. He also has a student's guide to vector calculus, if you just want that. But Daniel Fleisch, great one. Any second semester undergraduate text is a great introduction to Maxwell's equations, or just electromagnetics or electrostatics mostly. For that, there's a very, 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 very terse treatment on Wikipedia. If you want to go there, you can get that, but it's not all that helpful. I highly recommend MIT OpenCourseWare. Walter Lewin is my hero. He teaches great physics courses, and the 802 second semester freshman physics stuff is wonderful. You can even look up the article that was in Technology Review featuring a quote from me about how good his teaching is. He's just a great guy. He's really good at this. And if you want to get the MIT electrostatics course, 6013, that's on OpenCourseWare. Sadly, the electrodynamics 6014 is not on OpenCourseWare. I do have the course notes from 1978, if you'd like. But that's all I have. So with that, I'll take any questions. That's a differential geometry form. Yes?
How do we get the slides, please?
How do you get the slides? Email me.
Thank you.
Yes?
Several times he started to mention that a changing E field generates a magnetic field and vice versa, but then you stopped yourself. Could you comment briefly on that?
The circulation of H equation is Ampere's law, and the divergence equations are basically different ramifications of Gauss's theorem. Why do we call those Maxwell's equations?
Why what?
Why do we call them Maxwell's equations?
I can't quite hear you. Sorry. Oh, why do we call them?
If the circulation of H is varied, the circulation of,
They all
circulation
had
is
pieces
varied.
of them. They all had pieces of them, but Maxwell was the first one to put them all together and to put all the terms in place, including the things like the displacement current and all of that stuff. So they had bits and pieces. Maxwell was the first one to write them all down, tie them all together, and Maxwell didn't put them in this form, by the way. Maxwell had them as quaternions, didn't actually write them down as these four equations. There were 20 variables. There were different equations, actually. Heaviside finally wrote them down in this form, but Maxwell had them in his papers as these equations at different places. So I credit Maxwell with these equations because he actually wrote them first, although he didn't produce them as the final set. So yeah, the other people had the bits and pieces. Yes?
Your experiments for looking for magnetic monopoles, how would that affect the equation?
Well, then that del dot B would change to something else. It would be like, some other term that would be the, the magnetic charge density. The question was magnetic monopoles, how would that change things? So there would be a magnetic charge density, but that's been looked for a long time. Nobody's seen it. I kind of doubt it, but who knows? It could change.